Liz Holm is a professor of material science and engineering and the director of the Air Force Center of Excellence in Data-Driven Discovery of Optimized Multifunctional Material Systems at Carnegie Mellon University. Prior to joining Carnegie Mellon in 2012, she spent 20 years as a distinguished member of the technical staff at Sandia National Laboratories. Her research areas include computational material science at the atomic and mesoscale, and AI and machine learning for material science. Professor Holm obtained her bachelor's degree in material science and engineering from the University of Michigan, her SM in ceramics from MIT, and a dual PhD in material science and engineering and scientific computing from the University of Michigan. Professor Holm has received many honors and awards. She's a fellow of ASM International and the Minerals, Metals, and Materials Society, or TMS. She served as the president of TMS in 2013 and has been a member of the National Materials Advisory Board. Professor Holm has authored or co-authored over 175 publications. And please help me welcome Professor Elizabeth Holm.
Thanks so much, Chris. I'm happy to virtually be here. I apologize for the mysterious red flash that you may see as I'm transmitting. None of the IT professionals in my organization have yet been able to solve it. It only happens sometimes, and if we're lucky, it will just magically stop in the middle here. It often does. So let's share this screen with some slides, and that will be the main thing to look at anyways. Good. We seeing everything, Chris? Looks good?
Looks great. Thank you.
Great. Right. All right. Well, thank you all for joining us this morning. I'm very glad to be here virtually for such a really broad-ranging and interesting survey of where AI and deep learning are bringing us to in material science across different material systems, across different approaches. I'm going to speak about another area of material science, that of microstructural science. And so this is work that my group does, sponsored by a number of organizations, in which we are thinking about a different kind of data, not natural language data and not chemical structure data, but image data. And we know that as material scientists, we have a lot of image data. A number of the signals that we receive from our lab equipment are image type signals. And I'm going to specifically focus on microstructural images. Of course, the microstructure is that length scale between the atomic or molecular length scales and the kind of continuum scale of the part, in which there tends to be organization or structure that affects the properties of the material, the performance. And of course, that microstructure arises from the processing of the materials. And so when we take a picture of the microstructure, this middle length scale, we see evidence of what the processing of the material was. For instance, if we see dendritic type structures, we expect that this was a cast material. And we also see signals that help us understand how the material will perform. Will it be strong or weak, hard or soft? And I'll also add, of course, our images are multimodal, ranging from optical images through, of course, various electron microscopic images, EBSD, and also X-ray diffraction and other image-like signals. Now, in AI and deep learning, there have been a number of high-profile successes in computer vision, outperforming human experts at image-based tasks. And I show just one example here from the Google group. This is computer vision analyzing chest x-rays, looking for abnormalities and categorizing those abnormalities, whether it's pneumonia or cancer or whatever. And not only was the computer very able to successfully locate and interpret these abnormalities on chest x-rays, but the computer vision system outperformed radiologists at doing so. And so that's pretty exciting, the thought that we have a technique that is objective and repeatable, but also really accurate and useful to deal with image-based data. And so we'd like to bring that into material science. We have image data. So our goal is to apply the tools of computer vision to do for material science what medical imaging has done for radiology. So let's talk briefly about why we might do this in microstructural science. We have a number of tasks that we do. Some of these tasks are tedious and expensive, and we would like to replace human effort with computer effort, as we've discussed already this morning. Some of these tasks are hard, and we would like to have assistance in doing them. Others of them are tasks that we can't do any other way, and we'll talk about a few of those. But here's the kind of my laundry list, and you can look at this overview article in MetTrans that discusses most of these. We start from things as simple as image-based search and sort and classification, which we've talked about classification problems in other contexts already today. But we go through things like specification and qualification of a microstructure. Finding outlier microstructures is related to that. We think about autonomous analysis, novel characterization methods, instance generation. We'll talk about that in a minute. Of course, making those all important processing structure property connections. And of course, design optimization of microstructures, just as we've heard about design optimization of materials in the previous two talks. And finally, we won't talk about it today, but simulation surrogate is an important area for computer vision as well. That is being able to run some of the simulation types we use to analyze microstructures more quickly by learning them rather than running them with a finite element model, for example. The main tool for computer vision is convolutional neural networks. So, excuse me, the phone rang, of course, because why wouldn't someone call me right at this moment? Our main tool is convolutional neural networks. And the convolutional neural network is a pipeline that is a signal processing pipeline that has two jobs. The first is it takes an input image. Here I show on the left, this is the classic picture of a CNN. You'll see it all the computer science blogs. Takes an input image here of a car. And the first part of the pipeline is called the feature learning pipeline. This is a signal processing pipeline that goes through convolution, rectification, and downsampling steps in order to transform the digital image into a string of numbers, which we call the feature vector. This is the same as smiles or selfies. This is turning our data set, the visual data, into a feature vector, a representation that we can use mathematically in our machine learning. And if we're doing this right, if we're doing this set of signal processing steps right, the feature vector should be meaningful to the image. Unlike smiles or selfies, it is not reversible, for one thing. It sort of can be with generative or autoencoding methods, but it's not intended to be. What it is intended to do is capture the relevant visual information, the visual information that's important for the subsequent tasks. And so it's a little bit different there than some of the molecular encoders that we would have. The second part of the convolutional neural net is where the neural net actually occurs, if it does at all, and that's the classification pipeline. That's where we take the feature vector and do something with it, typically a machine learning task, the original of which was classification, and that's why it's often shown here as the classification pipeline. But we can use the feature vector for any kind of machine learning. We can use it for cluster-based learning unsupervised. We can use it for support vector machine learning. We can use it for random forest or whatever. It doesn't have to be a neural network. So in that sense, it's a little bit of a misnomer to think about a CNN. Now, the components of deep learning for image data, as the computer scientists practice it, include the convolutional neural network. Here I show VGG16. It's just one of many architectures for CNNs. Typically, you'll have millions of parameters that have to be learned in these deep learning systems. Millions of parameters means big data. And so typically one will train one's convolutional neural net on one of the big data databases of natural images. Usually there are some specialty databases as well, but there certainly aren't any millions of image materials databases. One that is often used is ImageNet, which I think contains about 14 million natural images of cats and boats and cars and so on. When we put these two together, we can get impressive results. This is the original NIPS paper that everyone goes back to in computer vision. The first result was to use the feature vectors, just that first part of the CNN pipeline, straight up as is, and compute visual similarity. Look for the differences between feature vectors. And so the images on the left, their feature vectors are the ones we're comparing to, and the images in the right-hand columns are the images with feature vectors most like the left-hand feature vector. So upper left, you see a purple flower, and this feature vector most like this image's feature vector are the feature vectors for these images going across the top here, which surprisingly or not, are all purple flowers. So the feature vector in this case seems to be capturing visual information that's relevant to the image. One of my favorite examples is the bottom row. On the left, the feature vector we're comparing to is this spotted hound dog, and we find a whole bunch of other pictures that, using feature vector comparison, that are spotted dogs. But as you see, they're spotted dogs in many different poses and situations, different magnifications, if you like, close up versus far away. So it's really, it's kind of remarkable, the quality of information that you can encode in a feature vector. The other thing you can do, of course, is do that classification pipeline, which these investigators did, and perform classification using the feature vectors. Up in the upper left, for example, is a dust mite. Even though it's only a partial image of a dust mite, the system is able to predict that it is most likely a picture of a mite. My favorite image, of course, is down here, this image that the humans claim. The ground truth is that this is an image of cherries. But the computer and I agree that actually the Dalmatian really stands out much more strongly. And that is the class that the computer chose, and I agree. So the computer in this case is making human-like qualitative judgments about the content of images. Qualitative-like, I should say, pseudo-qualitative, because of course everything is quantitative here. This kind of deep learning for computer vision enables just a wealth of computer vision tasks. We talked about classification. We can do segmentation, object detection, instance segmentation, crazy things like turn horses into zebras or turn ovals into turtles automatically, generative methods. So there's all kinds of things that computer vision can do, and that makes us want to do it for our data, but we have a problem. Our problem is that CNNs are trained on these huge databases, but we don't have huge databases of images. We're lucky when we have 1,000 images, more typically a few hundred of a particular material system. And so we want to use the learned parameters from CNN trained on natural images to address microstructural images. And we would typically retrain only the final machine learning layers of our CNN in order to do this. This is called transfer learning. And we could have a whole discussion on transfer learning, but the main thing I want you to know is it works well. We have found that the kinds of visual textures that CNNs learn to classify natural images actually help them do microstructural image-based tasks as well, very well. And so we're able to use transfer learning and not have to retrain our CNNs with millions of microstructural images. And when we do, we can do the same things that the computer scientists did for natural images. Here's an example of comparing feature vectors for visual similarity. This is a database you can look up. We have it up online. It's just a toy. It's of a set of ultra high carbon steel microstructures. There's about 1,700 of them. And one of the things you can do in this database is pick one of the microstructures and ask what are the most similar microstructures in this database. And here's an example shown where you'll see that indeed we see very similar looking to us humans micrographs of ultra high carbon steel, similar amounts of the various carbide phases, similar morphologies, and so on. We can also use visual similarity and feature vector comparison for material science tasks like quality control. Here we'd use visual similarity to a specified microstructure and say, do the top row of microstructures, for example, their feature vectors are sufficiently similar to the specified microstructure that we would say they meet specifications. The bottom row shows some out-of-spec microstructures, some microstructures sufficiently different that we flag them. And this is actually a job that our industrial partner does with humans. The human scans the microstructure looking for these regions that don't look the same as the rest. And of course, the human then decides what to do about that. What's interesting is the computer vision system, of course, speeds up that process, means that the human doesn't have to spend as much time scanning through stuff that all looks, fine, but also pulls out various kinds of out-of-spec microstructures. It's not just looking for one kind of defect, it's looking for any kind. And the human can then decide, is this actually a defect that I have to worry about? So this is an efficiency method for the human expert. The other first computer vision task is classification. And we can use computer vision as well to do classification of materials, images. Here is an example we did with NIOSH. Yes, that's the National Institute of Occupational Safety and Health, who are certifying our N95 masks these days. They care about airborne particulates, and in this particular case, airborne particulates that contain carbon nanotubes. These can be toxic. They can give a lung disease, much like asbestosis. And so they asked us, could we automate their pipeline of classifying these particulates? They take TEM micrographs of them, and a human has to literally sort through and find what class of particulate they belong in. Those classes are related to the toxicity. Some are safe and some are not. We were indeed able to train a computer vision system using transfer learning to do this task with about 91% accuracy, which was we were very pleased with, as were the NIOSH scientists, because as you can see, these particulates, they look very different from each other, even within a given class. And so it's nice that the computer can learn such a wide range, very human-like in its judgment. Here's an example where we go to that chest X-ray level, outperforming humans at classification. Inclusions happen when you process steel, when you make steel. Some of them are intentional and some are not. But the industry standard is to quantify them by finding them, surface inclusions, using SEM, scanning SEM. When the SEM sees a potential inclusion, it stops and does EDX, that is compositional analysis, which is a slow, costly step. Now we know there's some kind of composition information in the raw SEM images themselves. We know that because of the physics of SEM, how it works, that it interacts with atomic number. And so we ask, can we actually train a computer vision system to use the SEM patches directly instead of having to do EDX to do the compositional analysis? And this is a task that humans, we aren't accurate enough to do. And what we find is that indeed we're able to do this with an accuracy of about 75% on a 5-class classification, which is pretty good. On the right-hand side here, you see they all look like gray patches on a lighter gray background, but the computer vision system is able to classify them by composition. And even the misclassifications make sense. For example, the misclassification between alumina, calcium sulfite, magnesium sulfite is most commonly confused with these sulfides alone. And so we see that we're able again to do a useful task, in this case, one that even human experts struggle with. And this paper just came out in Frontiers in Materials. Finally, we can do classification on the pixel level as well. It doesn't have to be on the whole image level. When we do classification of pixels in an image, according to the constituent that they belong to, that's the task of segmentation. And those of us who are material scientists, probably many of us, spent some time during our research at one point or another with either, in my graduate student days, tracing paper and a pen, in my graduate students' days now, a tablet and a stylus, outlining the microstructural constituents. Well, we can train a computer vision system using supervised machine learning to do that task. And we see an example here again with our ultra high carbon steel database, where the graduate student has painstakingly annotated the different constituents. There are 3 different types of carbide plus the matrix material that have to be outlined. And we were able to train a computer vision system, a CNN, to do this segmentation task autonomously and do multi-component segmentation very accurately, certainly with accuracy equal to the graduate student. And that's nice, useful. We can do some different flavors of it as well. Here's a set of images that are low contrast. These are benitic steels. And we want to segment out the lath type bainite, which has very low visual contrast with the random bainite. In fact, the graduate student, to do the segmentation, the annotation, has to use EBSD as an auxiliary to check and see if it really is correct segmentation of the lath type bainite. But we're able to train the computer vision system to do this segmentation with excellent accuracy, despite the low contrast, and without having to resort to the EBSD for any ground truth comparisons. So that paper just came out last week, November 1st, Monday. Finally, here's an example of instance segmentation. Sometimes it's not a matter of finding out which pixels belong to which phase. For example, in this powder image, if we did segmentation, we'd say all the powder pixels are one phase. But instead, we want to find, in this case, all the powder particles. That's an object detection and segmentation problem called instance segmentation. Needless to say, it's useful for things like autonomous vehicles, where you want to make sure that you can tell the different cars apart from each other as you predict their interaction with the self-driving vehicle. We're finding all the individual particles here. This is, again, a task that is very useful. It's a very tedious task to do for humans, and the computer is able to do it with very high fidelity. I should mention it's not just the fidelity that's important. The computer is repeatable, which is not true of humans. It's objective, which is not always true of humans, at least objective with respect to what it was trained to do. And of course, I always say it doesn't graduate. It'll keep doing this forever. And that's helpful too. Let's see. I think I'm going to skip very brief. I think I'm going to go through this example very briefly so that we can get to some information about data sets. I want to just mention that it is possible with computer vision to come up with novel characterization metrics, new ways of looking at microstructures. I'm not going to go through this in great detail, but I'm going to talk, but the example is for powder materials, where we typically have powder materials characterized by simply the particle size distribution. But in reality, individual powder particles have many characteristics that are important to their properties, not just the size. And we can, for example, using computer vision, classify powders by the types of particles, the visual types of particles they contain, not just by the particle sizes. We do this by taking our images, extracting individual particles, either conventionally or using instant segmentation, grouping the particles by visual type using unsupervised machine learning, clustering, in this case, k-means clustering. We have 8 clusters of particles here, and you'll see we're capturing size. Cluster 0 is fine particles, cluster 7 is coarse, but we're also capturing surface relief, shape, the presence of satellites, and so on. And that means we can now characterize individual powders based not just on particle size, but on types of particles. And we can even find that this corresponds to properties. So we find that we can associate certain particle types with poor spreadability, for example, in additive manufacturing processes. I know that was very brief, but the basic idea is we can now quantify appearance of particles that include size and shape as well as other features, and get to a much deeper representation of microstructures than we could ever do by hand. Finally, of course, generative methods are kind of exciting in computer vision. This is an example that we've done on generative adversarial networks for creating 3-dimensional microstructures that are topologically and geometrically equivalent to the training images from experiments. These are solid oxide fuel cell electrode materials, complex 3-phase microstructures. The 3-dimensionality is critical to the performance of these. And we wanted to do, with our partners at NETL, the National Energy Technology Laboratory, we wanted to do surveys of the properties of these materials, computational surveys for which we needed lots of microstructures, more than we could get from our 3D characterizations in the lab. And so we trained up a generative adversarial network to create synthetic 3D microstructures for these materials. Not only do the synthetics, the fakes, look like the real microstructures, we can also characterize them as we microstructural scientists do by measuring their topology, their geometry, their phase fraction, triple junctions, and so on. And we can show that they reproduce the correct structures. Even more importantly, we can then test the properties of these microstructures and find that the experimental and generated microstructures occupy the same property space, property regime. Shown here, the most important property here is the current density. And we are able to show that we get a microstructure that is as realistic as possible. Now, I want to finish up with some new work that we're doing, because the question I always get from material scientists is, what do I need? What data characteristics do I need? 4 questions, really. What makes a good image to use for computer vision? How many of them do I need? How can I keep that number as low as possible? What should I do to keep that number low? And how can I tell if I've got enough for what I want to do? So I want to go through that very quickly here at the end. CNNs learn from visual features. Natural images have a certain set of characteristics. They tend to include one instance of the object, in this case, my cat Sahara. These objects have features at various length scales, whiskers, ears, tails, and so on. The field of view tends to be arbitrary. We never know quite how Sahara is going to orient himself. And however, we almost always have gravity as our orientation for taking the image. The result here is that we need lots of images, CNN images, to train a CNN. So we need to see Sahara in all of his possible poses to learn them. It's a little different when we think about microstructure. We purposely take images of microstructure to include many instances of the objects we care about because we want to get a statistical or a representative view. There are typically characteristic length scales that are better for capturing the things we know are important. This is sort of domain expertise issues. We take a standard field of view, usually plan view, and generally not oriented. So we can get all the orientations of an object. So relatively few images may be required to actually capture the full range of features. In other words, we have very data-rich images intentionally. It's why we capture them this way. So here, let's go back to these segmentations. I want to show you a different thing about these segmentations. Here's that low contrast segmentation. What I didn't tell you was this system was trained on 4 training images, 4. Remember, the grad student had to actually take these optical images and correspond them to EBSD images in order to get the segmentation. The CNN took only 4 of those annotations and came up with very good results. The instant segmentation, 4 training images. So it was a bad weekend for the graduate student when he had to outline all those particles. But after that, he was able to train the CNN to do it and do it in perpetuity. And finally, for the multi-component segmentation, 1 training image gave us these segmentations that I'm showing you. So let's talk about this data frugal nature of microstructural images. We're going to talk about the UHCS data set. It's 1,700 micrographs, as I mentioned, but only 24 of them have been annotated with their constituents. So we train on 1 image and test on the remaining 23 annotated images. And here's a few examples of excellent segmentation. We get really good IOU scores, especially considering how hard it is to segment that Wittgenstein type. But that's not what I want to talk about. What I want to talk about is what makes a good training image. And now we can tell. We can train on each of the 24 images in our set, test on the remaining, and look at our score, our segmentation score, the IOU score. And we see that here's the worst training image, the one that gave the worst score. Unsurprisingly, this image has only 2 of the 4 constituents. It lacks the Wittgenstein and network type carbide. So it was a poor training image. This is a better training image. It shows all the constituents and in a reasonable volume fractions, but it is at a magnification that is not the typical magnification for our data set. It's at a higher magnification. Here's the very, very best training image of our 24. And you'll see it's at the standard magnification. It includes all of the 4 constituents at representative volume fractions. And it turns out to be the best. All constituents present, representative fractions, morphologies, typical imaging conditions. In other words, a good image is a representative image. This is the image we've always tried to take. This is the image the expert would say is a good image. And so it doesn't give us anything surprising, but it quantifies the fact that what we've always said makes a representative image is indeed the important set of factors for using in computer vision as well. So we don't have to go back and do anything differently about how we take images. We just take our good ones. How many of them do we need? Well, here's an answer. I mean, I don't have a way to justify this other than to say that we have performed all of these tasks and learned that for segmentation, we can often get away with single image training images. For classification of images, we generally need more, typically 10 or more, sometimes as few as 5 or more, with data augmentation especially. And finally, something like a regression or a more complicated machine learning task, we typically advise that you're going to need 20 images per class or per type of image. How do we make sure we have as few as possible? What do we do for our images to make sure that we don't need more? The main things are we want representative images, as we discussed. We want the resolution to resolve the things we care about, the features of interest. We want to make sure the classes, if possible, can be told apart easily. That's going to give a better outcome. But within the classes, we'd like it relatively homogeneous. And finally, we'd like to standardize imaging conditions insofar as possible. And we can do some of that in post-processing, and we can learn some non-standardization too. But these are things that give us the best chance to have the smallest data set. And here's an example. where resolution is critical. As I said, that's one of those characteristics. For steel inclusion classification, we started out with 7,700 low-res images and got an okay classification accuracy. When we moved up to a high-res data set, we got much better. So you saw the previous example before. When we moved up to a higher quality data set, we had fewer images, but got better accuracy on our classification. And so that's, that's one of the rules of thumb. How can we tell if we have enough data? Well, you can't get information that doesn't exist. And so we want to make sure that we probe to check if the information we care about exists. And we do that in our group by performing a hierarchy of computer vision tasks on every data set. We start with clustering, we move on to classification, and then regression. We do this for our data sets, even if none of those are the tasks that are the ultimate goals for this data. This is just a way to see if we have information. And I'll show an example very quickly. This is a data set of high strength, high temperature steels. We have yield strength metadata, and we have very good quality images, but it's a small data set, only 16 images per alloy. The interclass differences are quite subtle. In fact, a number of the alloys have very similar yield strengths and very similar microstructures. And so we wonder, do we have enough data here to do the task we want, which is to associate the yield strengths with the microstructures? We start by doing clustering, and we indeed find that we are able to cluster the data and see visual clustering, in this case in a TS&E visualization of the data space. And that tells us it's promising. There's information here that distinguishes the classes of images. We can do classification. The student did a very brief classification and got 76% accuracy. I am entirely sure that if he optimized it further, it would be much higher. But the point is, still pretty hopeful. We are finding information in these images that allows us to tell them apart. And so when we went to our true task, that is regression, machine learned regression to predict yield strength from the microstructures, we got accuracy to within 15 megapascals for 92% of our images. So the data set, we checked to make sure it contained information about the classes. It did, and we were able to capitalize on that to do what we wanted to do, which is associate microstructure with properties. So in conclusion to those 4 questions, what's a good image? It's the one that you as a metallographer know is a good image. It's a representative image. How many do you need? It will depend on the task, but it may surprise you how little, especially when you add in data augmentation. How can I make sure that number is as low as possible? You're going to consider the factors that we mentioned here, the resolution, the richness, the inter and intra-class issues, and the imaging condition standardization. And then with a hierarchical examination of the data, we can tell if we have enough to do a task that we care about. With that, I'll put up my slide of the team that all has contributed to what you've heard about today. My group members, the graduate students, postdoc, and alums of the group who have gone far and wide, including to consumer product companies and so on, as well as our collaborators. We are computational material scientists, and we rely on our data contributors and collaborators listed here on this slide, as well as, of course, the support of our funding agencies. And with that, I am delighted to answer any questions. I'm going to pull up the question answer, and Chris, maybe you have.
Sure. Thank you very much, Liz, for a fantastic overview of microstructure and image processing. We have several questions in the Q&A, which I can kind of guide you through. So the first question is from Arun Bhaskaran. Is it appropriate to directly compare classification segmentation results obtained from transfer learning with similar results obtained when a model was trained from scratch with a larger data set? In other words, should the result from transfer learning be accompanied with additional estimates like reliability metrics to account for data size limitations?
I think that's a really interesting question, Arun. Thank you for that. We typically, in what we are doing, we are typically using human annotated segmentations, which contain biases and inaccuracies of their own. So our typical metric is we want to replace the human in the segmentation pipeline. And so we compare to the humans' results and determine if we're close enough. We have trained our own CNNs, rather small architectures with data sets that we've been able to do. For example, we did that originally with the steel defects data because we did have thousands of images there that we were able to work with. And what we have found time and time again is that inevitably transfer learning works better than from scratch, simply because we never have the depth, breadth, and number of images to train a deep learning network from scratch. And so I think it's an interesting thought of doing a like with like comparison, but we simply don't have the data set to train the same neural network that we would use in a transfer learning mode. It might be interesting to do as a toy problem, build a simple shallow neural net and CNN and try it both ways, in transfer learning versus not, but it won't quite get to what we want in terms of it's the deep neural nets that are so powerful.
Just to in on that that particular question, could you explore that by constructing a synthetic data set of microstructural images?
Yeah, I'm sure we could. We do some work with synthetic data sets for various reasons, not the least of which is we can get the ground truth really easily, right, when we build it ourselves. And that would be that would be a direction to go. The challenge, again, think about the natural image databases and the sheer variety of images. We would have to have a synthetic data set with that kind of richness, I think, to make it a fair comparison.
Right.
Yeah.
The next question is from Taylor Sparks. Hello, Taylor. Thanks for joining. So he says, great talk. What concerns do you have that GANs or other tools for data augmentation might actually heavily unbalance the training data away from the identical and independently distributed assumption? In other words, creating an echo chamber where our training data doesn't reflect the real world.
Yeah, that's a real danger. We can generate anything we want to, right? And then we have to check and see, does it actually fill the data space? One of the things we've seen in our GANs work, Taylor, and there's a fair amount of it out there now. We've been in the 3D space, but I think there's been some really nice, careful 2D work, especially coming out of Ohio State, for example, and other places. But one of the things we have seen is that GANs tend to reproduce average structures and they don't catch tails, right? Whereas often in materials, we care most about the tails. And so we do risk biasing towards the average. And as you say, denying the independently distributed assumption. They're not necessarily independently distributed. And we are also at risk of losing tails. And so I think that's active work in progress in that area, very much so. We know it's really, really easy to train AI systems to be to have blind spots that we are not aware of. And one of the most important things to do with generative methods is to make sure you look for those.
Great. The next question is from Dale Gaines, who's a graduate student at Northwestern. He says, are you able to get away with so few training images, like in the case of only requiring a single image for segmentation, due to transfer learning or data augmentation?
The answer, Dale, is both. The transfer learning means that we have a nice deep learning system that knows a lot about how images look and has the right kinds of filters to look for visual textures and edges and blobs and things. And so we have a system set up to be able to deal with images. And then we do use a bit of data augmentation for the single learning, say the single image learning system, because we do know that CNNs are not rotation or scale invariant. So we do want to make sure that we do some rotational data augmentation, some scale-based data augmentation in order to get the best results. That said, I didn't speak about it today, but our most recent work is working with scribble-based annotations, which means that we're not even annotating all the pixels in our training image. And in that case, we find that that combination of transfer learning and some data augmentation are enabling us to do this task with sub-single image ground truth data. So together, those two things are very powerful.
Wow.
Yeah, I was kind of blown away by that one when my graduate student said, look, we use 10% of the pixels in this image and we trained it well. So
amazing. The next question is from Wei Chen. She says, thanks for your wonderful talk. The techniques you showed are practically useful. It would be nice if they could be integrated with commercial imaging analysis software. And she wants to know, are there good amounts of interest from the industry side?
Thank you, Wei. And by the way, I'll see you at CMU next week. So we're having kind of the science virtual exchange this Friday and next Friday. I agree. I think that there's definitely commercial opportunities here. We certainly work with a number of industries who want to bring this in-house. We've talked with some of the microscope companies, for example, but I think they're working this method on their own because they have a different profit model than our group does, where we're interested in the material science outcomes. And so we do all our code open source. It's available, and contact me if there's any particular code that you're interested in, everyone. But I do think that there is substantial interest from the in our case, the metals industry, and you saw that in our list of partners. And like I said, I think there's some commercial opportunities in the imaging field, but those companies are keeping it more in-house.
So I have a couple of questions. So one is, and I apologize if you explained this and I just missed it, but you didn't seem to talk too much about specifically how the feature vector is constructed. I'm quite interested in that.
Yeah.
So can you say something more about that?
So sure. I mean, that's the black boxy nature of CNNs, right? Is that the CNN has learned the filters and the weights, and of course has this complex architecture. And there's huge amounts of what we call hyperparameters, which are things the human has to set that include all the architectural information, right? So for all that, we think of AI as getting us away from Edisonian exploration. When you create a CNN, it's an Edisonian creation system. Typically, you're trying to figure out what combinations of the signal processing steps are going to be most effective for the kind of data you care about. So there's that, and then there's of course all these learned parameters as well, millions of them that include filters and that include weights and activations and things. So that leaves this very mysterious. We start with an image, we end up with a vector. The vector has entries in it. The entries are meaningful. We know this, but what do they mean? And the answer is we can look at what they mean in some ways. I'm sorry I don't have it here, but one of the classic ways that one looks at this is by blocking out areas of an image and seeing if you can still tell what's in it. And so you can, for example, if I were to block out all the Wiedmannsstatten carbide, would the system still learn to segment Wiedmannsstatten carbide? If it couldn't, then we would say, it's looking at the right things, when it's doing that. But if it still could do it, we'd say, what's it looking at? Or a more typical example, if we block out the cat in the picture, does it still know it's a cat? No, so it's looking at the cat in order to make that. And of course, sometimes we find out that the system is not paying attention to the features we think it should. For example, it might tell dogs and cows apart because the dog pictures were indoors and the cow pictures were all in pastures, right? So it's not looking at the cow, it's looking at the grass in order to find cows. And so this is the great mystery of unlocking the black box, especially for transfer learning, where we actually are subject to the fact that the system isn't even trained on the types of images we care about. So I think that's, we have done a few papers on this, Chris. There's one with Julia Ling from Citrine in Facts, which Bryce is aware of and a co-author on, where we looked at things like filter activations in the CNN representations and showed that they make sense. but that's a post hoc analysis, right? It's saying the feature vector seems to be keying in on things we think are important too, but it's not pre-designed that way. It's just analyzing the fact that it
Okay,
does.
so if I understand, you're essentially, you don't include any kind of domain specific information in the representation.
Yeah, not in this representation. Now we do other things. For example, I have an excellent student working on abnormal grain growth where we are encoding the microstructure with graph feature vectors and using graph neural networks. And so that's definitely expert domain knowledge to create the encoding, the feature vector. Likewise, I heard a really interesting talk this week, in fact, at the TMS course that I was at, which includes constraining the physics allowed in a feature vector representation. In other words, requiring certain connectivities, for example, of the phases. And so we could use domain knowledge effectively here. Nothing that I showed you in this talk does.
Okay, great. That helps me understand a little bit better. Thank you.
Mm-hmm.
Okay, I'm sorry, I think we have to ignore the last question and move on. But thanks again, Liz, for a great talk.